Yes, very good. I'm glad to see you here bright and early at 10 a.m. As you know, yesterday, Matt did everything he could to raise doubts about the viability of isolated binary evolution as a way of producing two black holes. And therefore, I am going to carry on, and although I am not going to promise that dynamical formation mechanisms will allow you to realize all of your hopes and dreams, I will give you at least some ideas about why it is that this could be a more efficient way, potentially, of forming double black hole binaries. And what we're going to do is I'm going to start out by telling you some of the advantages very quickly about why this would be, some of the problems, potentially, with doing this in very dense stellar environments, and then we're going to get to some dynamical mechanisms, and at the end, I will see if I can give you a scenario in which it gives you the advantages, but not as many of the problems, because why not? So let's first talk about very quickly the advantages. So let's write down something here. The number density of stars in the solar vicinity is approximately 0.15 per cubic parsec. That is not very much. So this means that, for example, and ultimately I'm happy about this, our sun and all of the planets have remained undisturbed for their entire 4.6 billion year lifetime, even out to the tens of AU for the Kuiper Belt objects. Occasionally the Oort cloud will get brushed, but other than that, we're doing fine. But if we think about the number density in the center of a globular cluster or a nuclear star cluster, say it's the center of a galaxy, this can easily be greater than 10 to the 5 per cubic parsec. So, as I will elaborate upon, this gives you many new options for channels to form double black hole binaries and also double neutron star, but because LIGO has not been kind enough yet to discover neutron star plus X binaries, we'll talk about double black holes. So this is the advantage. The disadvantage is that there are very few stars which are in environments of this type of density. To get an idea of this, let's think first of all just about the Milky Way. Now the Milky Way has approximately 100 globular clusters. This is, of course, astrophysical accuracy. It's a bit more than 150. And let's say that they have approximately 10 to the 5 stars each. Average, which is not horribly far off. The Milky Way also has a nuclear star cluster with on the order of 10 to the 7 stars in it. So adding them up and realizing that 2 equals 1 to astrophysical accuracy, this tells us that we have on the order of 10 to the 7 stars in these high density environments, something like that. However, the Milky Way as a whole has about 10 to the 11 stars. So that means that for a Milky Way, approximately 1 in 10 to the 4 stars is in a dense stellar environment. If you go to ellipticals, where the specific frequency or number per mass of globulars might be 10 times what it is for a spiral like the Milky Way, maybe you boost that a little bit. That means that you have something on the order of 10 to the minus 4 to possibly 10 to the minus 3 of stars in a dense environment. So you have many new possibilities of new channels, but you have to be really, really efficient in order to take full advantage of them. Now with that in mind, I now want to talk about some of the particular processes that are involved and why it is that having high densities can be a great advantage. And for fun, and to try to keep you a bit alert, we're going to do this with a demonstration. So if you take an environment like what we have around our sun, stars are few and far between. You have singles, you also have binaries, of course, but they never meet each other. Well, on the other hand, if you're talking about an environment of this type of density, even at that type of density, it is actually very rare for 2 stars to hit each other. However, if you have a binary and you have a single star that comes by, those can interact in a way that more or less has the binary giving you an effective area equal to the area of its orbit, as opposed to the mere area of the star, which is tiny by comparison. Now there are a couple different things. In fact, there are going to be a few of these items that we'll try to give you physical demonstrations of in sequence, so then you can bury yourselves in the later equations with a certain image in your mind. One of the interesting points here is, suppose that you have a dense stellar system and you have a binary. Now you can divide these binaries into two types, soft binaries and hard binaries. Soft binaries are very wide, and because they're very wide, they move very slowly, and if the internal energy of the binary, roughly, is less than the typical kinetic energy of a third star that would come by, the net result of the interaction is to ionize the binary. So it would be something which is separated. Therefore, dense stellar systems have typically only hard binaries. So these are binaries that are such that their internal energy is greater than the energy of the field stars coming by. Now let's suppose that you have an interaction between these. So we'll start out with some sort of binary like this, and we have a third object coming in. We're imagining three equal mass objects. You might hope, of course, that this would be something that would be stable, but in fact it really isn't. And after enough orbits that are fairly chaotic, they end up having one of them being flung away, and the other two are now in a tighter binary than they were before. So this is a process, actually, that ends up giving you tightened binaries, which means that if we have our three equal mass objects and lots of interactions, we're going to tighten more and more, and therefore, even if the binary started out too wide for gravitational radiation to be interesting, eventually it can get tightened enough that it can merge. So this is one aspect. Now there's another thing I'd love to be able to demonstrate here, but it would involve a heavier star. Here we've basically got three equal mass objects. So unless anyone happens to have a heavier ball around to help with the demonstration, I don't know if we're going to be able to do much about that.
Cool. Completely by chance.
Yes! Amazing! How about that? Would you care to come up and demonstrate?
Oh man, of course. Thank you for allowing me.
All right,
Anyway.
and so here we have a heavier object. So here we're going to imagine starting with a binary of two, say, ordinary stars. And then the other thing is a black hole. And that is going to come in. And as it comes in, there's all sorts of interaction that occurs. Again, this kind of weird stuff that happens. And eventually one of them gets flung out. And the net result is usually going to be that the final binary consists of the two most massive of the three original objects. This means that even if black holes start single, they're typically going to substitute in, and then later perhaps another black hole could come in. And now, the next phase of the demonstration, so I'll take the heavy object, I'll give you this, is going to involve the next thing up here, and I will go through this in some more detail, the Cosine leadoff resonance. Now the idea is that what you are going to end up with eventually is a stable hierarchical triple. That is to say, you're going to have an inner binary and an outer tertiary, a third object, which is moving far enough away that it's not dynamically unstable. This is something you could imagine evolving from a triple system, but for reasons I'll get into later, that's actually a bit more of a challenge. Instead, it is more likely, especially in a dense system, that this could come from a binary interaction. And so, if we have our binary there and our binary here, and this is involving a black hole, then what you're going to get now is all sorts of strange things. So here we have the fourth object, and one of them gets flung out in order to bind things. And what we end up with is a binary here and a distant object here. Now, as you can see right now, the orbits are nearly orthogonal to each other. So this is a high inclination orbit. Over a long period of time, the inclination can change, so it's a bit more of a steeper angle, and you see that the eccentricity of the inner orbit, in fact, goes up. And then back in the cycle, where it goes to a larger inclination, you have a lower eccentricity, and then back to the smaller inclination, higher eccentricity, and here, if the pericenter is close enough, gravitational radiation can grind down the binary and eventually cause a merger. All right, let's thank Cosine. Thanks, man.
Thank you.
All right, very good, very good. I guess you have next to here. Okay, yes. So that will be the enjoyable part of the talk. Now, if what we're going to think about in more detail is some of the numbers. Okay, so we're going to begin with the binary single interactions. Remember, a couple of key qualitative points here, as we were demonstrating, is that if you have a hard binary, the interaction tends to harden it, in other words, tighten it further. And if you have a massive object that is involved, it is very likely to end up in the final binary. Especially if you have something like a black hole involved with ordinary stars in a globular, which are much less massive, it is very likely indeed the black hole will end up in that final binary. By the way, for those of you who are interested, those two trends, the tightening and the idea of the heavy things ending up, can both be derived from thermodynamic considerations to a large extent. However, the three-body interactions themselves are chaotic in a formal mathematical sense, which means that these are only tendencies, and it is not easy to write down some prediction analytically of what a given system will actually end up doing. With this in mind, let's now think a little bit about what is going to happen if you end up with a binary single interaction. There's some things you can think about here, and we'll imagine that we've got, let's say, a binary here, and we've got some characteristic separation A, and we have another object which is coming in. If this object comes in at a separation from the center of mass, which to make it unequal mass will do this, is much greater than A, then the binary is barely affected. The binary as a unit may be affected in the sense that the binary tends to be heavier than the average star, and therefore it will sink into a region of high density. But if the passage is far too far away, then it's not going to have much of an effect on the internal properties of the binary. But if it is on the order of A, then it can go in, and as we were demonstrating, it can actually be a very involved interaction. In other words, it's not just one dynamical time through. It is commonly something that could be tens of dynamical times, scrambling the system up to an extent. If we think now about the properties of this, let's suppose that, for example, A is equal to 1 AU, and let's suppose that the mass, so this is going to be the total mass of the binary, is on the order of 60 solar masses, because that apparently is everyone's favorite number these days for double black hole binaries. This means that the speed with which these things are moving together, so that the V, which is going to be, of course, square root of GM over A, for what it's worth, by the way, rather than remembering the god-awful value and units of G, you can remember that the Earth goes around the Sun at 30 kilometers per second, which means that 30 kilometers per second times the square root of 60, and so in this particular case, we're talking about something that is on the order of, and I'm not trying to be precise here, about 250 kilometers per second. In a globular cluster, the typical speed in terms of the velocity dispersion might be something like 10 kilometers per second. This is much larger than this, which means that if you want to actually do the calculation, you are starting in the gravitationally focused limit. And what we mean by this is that the passage of this is going to be deflected significantly by gravity. This means that the effective cross-section is not, in fact, quadratic in A, it's linear in A because of the effective focusing. And in that limit, the cross-section, which I will write with a capital sigma, because lowercase sigma is usually reserved for velocity dispersion. So this is then going to be 2 pi times A times GM divided by sigma squared, and so the velocity dispersion is sigma, so this is kind of comparable with the speed of infinity. And this gives you a particular value. And then the encounter rate you have, if you write this as an inverse time, is going to be the number density times sigma, the cross-section times sigma, the velocity dispersion. And this turns out to be on the order of 10 to the 7 years times n over 10 to the 5 per cubic parsec. So tau is 10 to the 7 year centus, times minus 1, times A over 1 AU to the minus 1, times M over 60 solar masses to the minus 1, times sigma over 10 kilometers per second. Okay, now, this is small compared to the age of the universe, and it means that these, in this kind of environment, with this type of semi-major axis, you're going to have a lot of encounters. So this is quite promising. But we're not there yet, because simply having a lot of encounters is insufficient if what you want to do is harden the binary. Imagine, for example, you were to calculate the rate of encounters with dust particles in the ISM. It would be a huge rate, and it wouldn't do squat to your semi-major axis. So you need to actually figure out something else, and that is, how long is it typically going to take to interact with enough mass that you can E-fold down the semi-major axis? You take whatever your initial semi-major axis is, the characteristic time. Now that turns out to be independent of M. Why? Because the rate of interactions goes like 1 over M. Sorry, so the rate of interactions goes like M. The time goes like 1 over M. But you need to be able to interact with of order at 0.3 M, as it turns out, in order to reduce the semi-major axis. So it's actually nicely cancels out, and what you get is that the time necessary to E-fold, so in other words, again, to reduce by order factor of E, is on the order of 2 times 10 to the 8 years times, now I'll write rho 5 to the minus 1, where rho is equal to 10 to the 5 solar masses per cubic parsec times rho 5, so it's kind of scaling, times A over 1 AU to the minus 1, and then times sigma over 10 kilometers per second. So I'm doing all this again for globular clusters. And you may remember that Matt said yesterday that if you take a circular binary of 230 solar mass black holes, you need to get it to something like 50 solar radii. For those of you who don't think it's solar radii, 1 AU is approximately 200 solar radii. So that means his 50 solar radii is about a quarter of an AU, and using your mighty powers of mathematics, you discovered the answer would be about 8 times 10 to the 8 years. Still comfortably less than 10 to the 10 years, the Hubble time. However, it's actually much better than that in terms of the speed with which this will occur. That's because, again, if you think about how those bizarre, weird interactions we were demonstrating go, it would be a high-order miracle if the interactions managed to preserve the circularity of the binary. In fact, relative to some reference plane, the inclination will tilt, the eccentricity will change, and the semi-major axis will change, all as a result of these interactions. And as you know, for a fixed semi-major axis, the time to merger is very much shorter if you have a significant eccentricity. In fact, the gravitational wave time, and I won't bother, there's a prefactor of order unity, is going to be something like a to the 4th times 1 minus e squared to the 7/2. And there's a mass factor as well. So this means that if you can get to a high eccentricity, then you can merge even if the semi-major axis is in fact not all that small. And it gets even better than this. If you think about the interactions of 3 equal mass objects in the binary singlet interaction, you find that if 3 equal mass, then if you do this many, many times and take snapshots of the eccentricity of the binary after the interaction is finished, you find that you end up with something called a thermal distribution, where the probability of some eccentricity is 2e, which is nicely normalized from e equals 0 to 1. But when it comes to having a massive binary and smaller things interacting with it, pioneering work by Quinlan in the 90s showed that there is in fact a greater tendency towards higher eccentricity than this would indicate. And this means that rather than having to wait until your semi-major axis is a quarter of an AU or 50 solar radii, you can actually get things into a state where the merger is imminent, depending on your definition, much more quickly than that, and in a much larger separation. So this is the basic idea that we're having. Now those eccentricities, of course, since as you remember, gravitational radiation circularizes a binary. If you have the binary and it's no longer interacting with anything, and then it just proceeds, it's going to circularize. Even if you have a so-called high eccentricity, for example, 10 AU and an eccentricity of 0.999, the pericenter is so large compared to the distances you need for significant LIGO detection that it's likely to be very close to circular. So even in that case, it's likely to be circular.
Can I ask a kind of possibly very basic, stupid question? But this is all Newtonian dynamics, which is time reversal symmetric. So this trend towards hardening
Yes.
is obviously due to some initial condition being, well, special. And you mentioned thermodynamics, so...
Yes, absolutely, and this is a very good point. Because it is, as you say, completely time reversible, we can take our interaction that hardens a binary and exactly reverse it from when the final object left to infinity, and we could end up, in fact, opening up the binary. We could soften the binary instead. So, number one, it is in fact true that there is always a possibility that you're going to end up with a wider binary than you started with, even if the binary was hard. But it can be thought of in certain ways as akin to changing entropy. So in the same way that you can have a system, even in classical dynamics, that starts out with a high entropy and evolves to low entropy because things are completely reversible, the probability is very, very low of this. It's not that low because we're only talking about 3 objects as opposed to an Avogadro's number worth of objects. But that's the basic idea. So there's more phase space to eject something and have the single final object have a higher energy than when it began. And the same thing is also true. This is also an argument you can make for why it is that heavy things tend to swap in. Is that having a light thing sailing out with a certain amount of energy, it has a larger momentum for the fixed energy, and that means that it can explore a greater amount of momentum space than the heavy thing would. So these, as they say, are tendencies. When you get to large mass ratios, they're very strong tendencies. When you get to extremely hard objects, they tend to be quite strong tendencies as well. But it's statistical.
Sure, and this depends on the cluster supplying these informing, well, these stars that approach the binary at a particularly low velocity?
As long as the kinetic energy of the interloper star, the third star, is significantly less than the internal binding energy of the binary, then you have a hard binary, and a strong statistical tendency is to harden the binary after an interaction.
Okay, but there's a specific initial condition.
Well, when you say specific initial conditions, all you really need is the energy ratio.
Sure.
That'll do it. But in terms of this is one of the reasons that I was also writing this. So let's say we happen to have our binary like this. Now these are also massive objects, and so for a given speed, their binding energy is much, much greater than it would be for a low mass object. If we're talking about something in AU or even 10 AU, the ratio between the binding energy and the kinetic energy is huge.
Sure.
So it's a strong tendency and not something that has to be fine-tuned.
Oh, I'm not saying it's fine-tuned, but you're taking advantage of all these slow incoming stars from the cluster.
Yes.
Which is correct, given that they actually exist.
Yes.
No, but maybe in order to clarify, usually what you do is you take the size and the mass of the cluster, and then you estimate the average velocity of stars. And at a given point, one of the binaries will bind and will be faster. Okay? If this will happen, and well, this will happen sooner or later, right? When this happens, the process kicks in, and it's a sort of a runaway process.
Yeah.
So it's basically, I mean, unless you start with a cluster that has 10 to the 5 kilometers per second as sigma, and we don't have them, or it's pretty close to a black hole, then it's always going to happen, right?
Sure.
Because let's say all the stars are moving slowly.
Yeah. Sure. I mean, I'm not disputing that it exists, just that gravitation and entropy do interesting things together.
Yes. Yeah, they really do. Particularly when you realize that clustered things have higher entropy than non-clustered things, which is a bit of a poser initially. Yeah. Okay, so that was the idea of binary single interactions. Let's now talk about another mechanism here, the Cosine-Leadoff resonance, which has acquired phenomenal popularity in the past several years among the exoplanet community. In fact, it seems that all processes are now being explained by the Cosine-Leadoff, which is not entirely an exaggeration. Maybe it's an exaggeration by a factor of 3, which is not terrible. Okay, so the Cosine mechanism. Now the Cosine mechanism, and we demonstrated this before, is let's suppose that you have a binary, and we'll imagine that this is the initial plane of interaction, and we have another object here. And so we've got something going around this way, something going around this way, and so the initial relative inclination is fairly large. This mechanism was actually discovered independently by Cosine and Leadoff with a couple of different ideas in mind. One was Cosine wondered why it is that we don't have any high inclination comets interior to Jupiter's orbit. What Leadoff wondered is, given that there were satellites which were being launched, which were more or less moving perpendicular to Earth's orbit, he wondered how would the orbit progress? And the answer turns out to be that over times that are long compared to both the outer orbit and the inner orbit, and therefore this is, at least in the standard quadrupolar approximation, called the double averaging scheme. You average over the inner orbit and the outer orbit. The averaging means you're time steady in some sense, which means, deep insight, that the energy is conserved, and therefore the semimajor axis is conserved. So if you have some semimajor axis A here, then the system can basically do this, where the inclination goes down and up to limits that depend on the angular momentum ratio between the outer object and the inner binary. And as it goes down, the eccentricity goes up. In the classic sense, the very restricted three-body situation, for example, the Sun, Comet, Jupiter, which was Cosine's application, you find that it is the component of angular momentum which is perpendicular to the tertiary orbit that ends up being conserved. And so if you started off at 90 degrees, that would actually give you a 0 angular momentum component, which would mean that if it starts tilting away, the eccentricity would have to go to 1 in order to conserve that component of the angular momentum. So the answer to Cosine's question is that if you had high inclination comets inside of Jupiter's orbit, then they would evolve to systems which had low inclination and high enough eccentricity, the comets would actually hit the Sun. We have probably seen those now. So a number of the SOHO comets, which are in fact sun grazers, may well have been produced by this mechanism. And the answer to Leadoff's question is bad things for the Vanguard satellite. For example, if you want to make a real satellite instead of an artificial one, if we were to imagine that at some point we as a society get bored enough with our other activities that we become interested in putting the moon into an orbit which is absolutely at 90 degrees relative to Earth's orbit around the sun, and then we just let things progress gravitationally, the moon would hit the Earth in 6 years. Now, this is fascinating, right? Why do we care about this in the context of black holes? Well, the answer, of course, is that if we can somehow get a system in which we have 2 black holes, like this, and then the third black hole out here, or it doesn't even have to be a black hole, it could be an ordinary star, then it could well be that although the initial system has a large enough semimajor axis and a low enough eccentricity, that it will not merge by gravitational radiation within Hubble time. The influence of the outer object could cause this to do the up and down inclination, and at minimum inclination and maximum eccentricity, it could be that the pericenter passage is small enough that gravitational radiation shrinks the binary, as Massimo displayed. So this is a way potentially of taking systems that might not favorably merge into ones that do favorably merge. Now, there are a couple things that we do have to keep in mind here. First of all, you might imagine that this is a process that could equally well operate in the field. When we think about binaries, we think about two stars. If these are two massive stars, it is, however, very difficult to see a third star if it is around there. And as observations have improved, people have realized that a decent fraction of so-called binaries actually have a third object, maybe as much as 10%, perhaps an even slightly higher fraction for massive binaries. So this might give you extra hope. Perhaps in the field, with no other stars nearby, a triple system could evolve to two black holes here and one object here, whether a black hole or not, and these could be coside into happy union. The challenge, however, is that black holes are very small compared to their main sequence predecessors, and even smaller compared to their giants. For example, one idea that has been proposed is that type 1a supernovae are caused by colliding white dwarfs, which run into each other because they're in triple systems and end up getting coside into that kind of merger. But a more detailed examination shows that this is a very unlikely channel, because if they were initially in a favorable configuration, then they would just run into each other in the main sequence, or possibly as a giant. So they never get the opportunity to become white dwarfs. There are narrow regions of phase space where it is possible to not collide on the main sequence or giant branches, but do collide on the white dwarf branch. Because of mass loss and things like this, they can set the system up in different ways, but they're rare. And that's why, when Massimo and I did our demonstration, we were thinking instead more about a dense stellar system and a binary-binary interaction. Because in that situation, you can have your 10 billion-year-old globular cluster, lots of binaries around, maybe some black hole binaries, and they never have to be anywhere near each other when they're on the main sequence. And therefore, the interaction can in fact produce a stable hierarchical triple with a decent chance of being in a cosine configuration. Incidentally, of course, if binary single interactions are chaotic, you better believe that binary-binary interactions are chaotic. And binary-binary interactions have a lot more parameters you have to worry about. You have to worry about two different Semimajor axes. You have to worry about four masses. You have to worry about relative inclinations of the binaries and the eccentricities and so on. So these have not been examined in nearly the kind of detail that binary singles have. But when people have looked at binary-binary interactions, they find that in something like a quarter of cases, you end up with a stable hierarchical triple. And of those, tens of percent could be in a cosine type configuration, so it's not that improbable. The other thing is the question of the effect of precession. Because as I'm describing this, I'm not telling you anything in particular about these systems. And this, as I said, is going on over quite a long time. And by a long time, I mean that the time, this cosine time, some people prefer cosine leadoff, which is also fine, is like this. So I'll describe what these terms are in a second. Okay, binary orbital period, mass of the binary, mass of the tertiary, semi-major axis of the binary, semi-minor axis of the tertiary. And so if you put in things like, typical masses and whatever, and separations, this is something that could comfortably be hundreds or thousands of years, which is a very short time dynamically. But there are other processes that could be faster. They could actually shut off the cosine mechanism. As an example of this, I know we're all black hole enthusiasts here, but you may know that Uranus is tilted by 98 degrees compared to its orbit. You may also know that Uranus has moons. Moons that in fact are orbiting in the spin plane of Uranus. So 98 degrees tilted with respect to the orbital plane. Now if you think that through, about the cosine mechanism, you'll realize that this is in fact a tremendously cosine favorable configuration. And indeed, if nothing else were going on, poor Uranus would have merged with its moons a long, long time ago, and yet it has not. So we have to wonder why that is, and the reason is that Uranus also spins. It spins enough that Uranus is oblate. The oblateness of Uranus means that there is a precession that is induced on the orbits of these moons. That precession is much faster than the appropriate Cosine time. Therefore, the Cosine mechanism is shut off. Here, we're not talking about oblateness, but we do have post-Newtonian precession, so general relativistic precession of the pericenter of the orbit. This turns out, and I did some work on this in 2002, it turns out to mean that you don't necessarily get to the maximum possible eccentricity that you would if you had Newtonian point objects. There's an upper limit given the properties of the system. Nonetheless, it is still the case that you can manage to evolve to a high eccentricity, a low pericenter, and therefore a short gravitational wave time. And then the other point to make about this, just kind of quickly, is when people talk about things like this and kind of sort of standard mechanisms, of course there are high order terms as well, which is something people have known for a very long time. And these are again being brought to bear on certain exoplanet questions. For example, if you do not have a situation where the outer object is completely dominant in its angular momentum, then unlike in the standard approximation, which is that the orbit of the outer object is unchanged throughout the entire cycle, the outer object can change its plane, and this can actually allow you to get to higher eccentricities. If the system is somewhat compact, still stable, but kind of on the edge, then you can even have situations in which you can have a plunge to a very, very small pericenter without getting to an intermediate pericenter. So in other words, it can go from a very broad, large pericenter to on the next passage something that's fairly close. So this leads to interesting dynamical effects potentially. Okay. Comment now about recoils, just because this is something we are being compelled to consider. There are two types of recoils that can exist in these systems. So one, if we think back to the binary single interaction and pretend that we live in a happily 1687 world of purely Newtonian interactions, then the tightening of the binary means that you end up with the binary having a greater binding energy than it did before, by definition. That energy has to go somewhere, because in the Newtonian case, you have a complete conservation of energy. There's nothing being taken away to infinity. It's all contained within the two systems, the single and binary. But where does that go? It goes into recoil. So effectively what it means is the single gets an extra kick, so the single is moving faster than it was before, and by momentum conservation, so is the binary. Now if the binary and the single are in a system that has a shallow enough potential well, it is possible that the binary as well as the single could get kicked out of the system. Then it wouldn't have any more interactions, because it would not be in these high density regions. This is something that was examined a long time ago. There's a nice paper by Portuguese Varda and McMillan in 2001, which suggests that in fact most mergers might be happening outside of globular clusters for this reason. However, it's much easier to stay in the cluster against Newtonian recoil if you've got heavier black holes. Much, much easier in fact. And 30 solar mass black holes interacting with 1 solar mass stars are there to stay against Newtonian recoils. But that's not the only recoil we have to worry about. So if we're thinking about the process of hardening a binary to merger, that's fine. That's all we do have to worry about. But if we'd like to get greedy, as I occasionally have in my papers, and think about the process of having continued mergers. So you have two black holes that do their thing dynamically, come together, merge, form a bigger black hole. Now that black hole swaps into a binary and eventually goes through a similar process. For that to happen, you need to be able to hold the merged product inside the system. Well, you may have heard that in 2004, 2005, and since then, there have been some substantial improvements in numerical relativity, which have in fact given us good indications of the gravitational wave recoil you get from the mergers. Now that recoil for the systems in question is going to be something on the order of between tens and potentially thousands of kilometers per second. This would require the proper spins and so on. But it's possible. And even tens is kind of a challenge for globular clusters. A dense globular cluster might have an escape speed of 50 kilometers per second. A nuclear star cluster, like the one in our Milky Way or other galaxies, can have an escape speed of hundreds of kilometers per second. And if you have something, say, in the very early universe, a very dense cluster, maybe it can get up to 1,000 or so. But nonetheless, equal mass mergers are things that are challenging to keep in these systems. If you have a runaway set of mergers, where you have one object gathering up a smaller object and then another smaller object and so on, and therefore most of your interactions are between a quite heavy black hole and one that is much less massive, the recoil is, of course, small. I mean, imagine throwing a dust particle into a black hole. You would be surprised if the black hole were then kicked out of the globular cluster. So this means that if you have runaway growth and you have a mass contrast, a mass ratio, which is substantial, the black hole is there to stay. But for comparable mass mergers, it's not easy. So my guess is, in systems like this, it's likely to be a one and done for a comparable mass merger, unless you get very, very lucky. For example, non-spinning black holes of exactly equal mass have zero recoil by symmetry. But unless you've got a special situation, it's not going to be very easy. Now, the last thing I want to talk about is the best of both worlds. So the thing that I kept up here from my initial discussion is that the fraction of stars that are in these very dense stellar systems where you have all these lovely processes is very, very small. And so this is therefore the tension. That gave an indication of why it is you need very special circumstances for an isolated binary to evolve to two massive black holes. Well, it's two black holes at all that can merge in a Hubble time, but especially ones that are on the order of 30 solar masses. And so here's a situation where as long as you can get a black hole of 30 solar masses somewhere in the cluster and another black hole of 30 solar masses somewhere else in the cluster, then they will find each other. But it's very rare. So essentially you've got a situation where it's much easier per stellar mass, but you don't have that much stellar mass. Is there a way, possibly, of getting the best out of the both possibilities? This is one of the things that we talked about I'm one of the et al. So we were thinking about the prospect of having potentially very massive black holes coming from standard stellar evolution, inspired by the observation in 2010 by Crowther et al. Of several very massive stars in a star-forming knot called R136 in the Large Magellanic Cloud. We were wondering, what if you just can form really, really massive stars and they form really massive black holes? What are the prospects for merger? A lot of the pure, isolated binary stellar evolution mechanisms don't really look all that promising. There are these many doors through which they have to pass, as Matt described. But we can remember that stars in general, and certainly massive stars, do not tend to form in isolation. Let's suppose, for example, that you have two 50 solar mass stars or 200 solar mass stars. When they form, they are highly likely to be in stellar associations or open clusters, rather than just by themselves. Now that means that they are not, in fact, truly isolated, at least for as long as the association or open cluster lasts. Now, if they happen to be in a dense stellar cluster, they're done. They're in great shape. Is it possible to use these sorts of systems and the dynamical interactions where, I remind you again, most stars form in these sorts of associations? So you're already tapping into not 10 to the minus 3, but, tens of percent of all stars. So is there a way of using this? Well, all these processes will still work. So you could, for example, have your massive binary, and you have a lot of other stars passing through. Great. Now, what are you going to have? Well, the number density you have is obviously going to depend very much on the system. So there are open clusters that have very low number densities, and then you have number densities that can be much higher than that. For example, R136 or the Archers or the Quintuplets clusters, which are in or in the vicinity of our Milky Way, can be 10 to the 3 to 10 to the 4 per cubic parsec, maybe even a bit more than that. Now, these are not clusters that are going to last forever. They might last 100 million years. So you have a shorter time that you can do this. Also, if we now go back and look at some of these formulae, what you see is that if we're talking about this kind of density and call it an average of maybe a solar mass per star, just give it a number, we can see up here that if we're just taking this number directly, then this density is down by 1 or 2 orders of magnitude. It looks like you're kind of close. Remember, however, that this is something that is really an overestimate of the time needed to drive something to a merger by binary single interactions, because you're also driving the eccentricity up. So you can probably take an order of magnitude off of that, and it means that the clusters that last for hundreds of millions of years, and there are plenty that we know of, really might be good options. Another possibility is that at some point you can get into one of these Cosine configurations. Maybe another binary comes in and one of them is thrown out and the other one is maintained in the hierarchical triplet. It'll be a lower mass star, but it will be able to drive the system in these eccentricity inclination oscillations. So this might be a way of, as I say, getting the best of both worlds. You have a substantial fraction of stars and a high efficiency with which you might be able to generate double black hole binaries. Thank you.